Greeting from Hong Kong. I am Jun Chen, a PhD candidate from School of Architecture, the Chinese University of Hong Kong. I'm going to present a case study about the collaboration between an emerging Chinese structural engineer and a Chinese architect. The focus of this case study is not the built form itself, but rather the people who designed it and the way in which the collaborative design process is manifested in the final outcome. The creative potential of collaborations among architects and structural engineers has been well recognized over the past decades. However, a linear design approach is widely applied in design process in China, in which architects would first finish a schematic design, and then an engineer from a large design institute would propose the structural solution. Only a few Chinese architects and structural engineers take advantage of collaborative design process. One notable example is the collaborations between an emerging Chinese structural engineer named Zhang Jun and many star architects. Through archiving all projects of Zhang Jun, we noticed that an open-ended design approach is emerging. Taking soft Matter Pavilion as an example, I will present one of models of collaboration developed by Zhang Jun and Chinese architects. Soft Matter Pavilion was built for an outdoor exhibition which was located in Shanghai Lin Gang New City, one of the largest reclamation areas in history. To respond to the ambiguity between nature and the artifact of the site, the architect proposed a basic architectural prototype, canopy and a column. The canopy is made of polyurethane foam. When it is sprayed, polyurethane foam rapidly hardens and expands, getting a bubble-like texture. And a cloud-like shell with the unfamiliar texture and thin columns together shows a mysterious visual effect. The structural engineer firstly attempted to find form based on mechanical design optimization. He considered minimum columns and curved shape of canopy as constraints to find form by rhino, grasshopper, and a kangaroo. A pincushion surface was found. However, its regular surface is far different from the expected irregular surface. Instead of searching for other schemes by mechanical design optimization, the structural engineer paid attention to questions related to material design and construction process. Polyurethane is light, but its material strength is too low to be a structural material. Meanwhile, how to not use complicated formwork during construction is also an issue. In this regard, the structural engineer proposed a scheme of material design that composited polyurethane with nylon net, which increased elasticity modulus and the tensile strength. Based on the method of physical model making, the structural engineer proposed the first scheme for the construction process. Firstly, distribute objects like yoga balls on the ground, covered with a nylon net to get the desired form. Then spray polyurethane foam on nylon net. Finally, lift the canopy up to the top on columns after polyurethane foam hardened. By testing the first scheme of construction method, the structural engineer noticed that nylon nets were not well tensioned. Meanwhile, the structural engineer and the architect together tested the lowest properties of the composite material through an experiment of brittle failure. Based on previous tests, the structural engineer made mechanical deduction to solve problems. Firstly, imagine that deformation and internal forces of nylon nets are caused by self-weight and external concentrated forces. Secondly, assume that there is no deformation and extra internal forces in the polyurethane shell when it is hardened. And finally, when polyurethane foam is hardened, remove pre-stressed seam forces so that axial forces in the nylon nets are transferred to polyurethane shell as compression forces. In this regard, he proposed the second construction method. Firstly, tighten nylon nets on the top of steel frame, distribute yoga balls on the top of nets, and hang weight on yoga balls, and get irregular curves. Then spray polyurethane foam on the bottom of nylon nets, then lift up and flip over the hardened shell, and spray the other side of nylon nets, and finally connect steel frame with steel columns. The problem is a crane is needed for flipping over the hardened shell. At this stage, the architect made the decision to give up the initial idea of the clouded-like canopy and make the initial form upside down. This decision not only canceled the need of a crane for flipping the canopy, but also made the shell resisted deformation of dead load during the construction process. In other words, the final form follows forces in the construction process rather than a predetermined idea. After the design of the irregular shell, issues of steel structure came to foreground. By mechanical design optimization, the structural engineer designed 6 solid steel columns, positioned on the edges with a maximum corner cantilever of 5 meters. In order to prevent deformation of the steel frame during the construction of the shell, the structural engineer also introduced 4 pairs of curved rebars to pre-stress the shell. The tensile force of the nylon nets during the construction was transferred to the steel frame as axial forces, which reinforced the steel frame. The design process shows a mode of dialogue, architect and engineer as equal partners in discussion. The structural engineer is neither wholly creator nor solely problem solver, but instead operates at their intersection and contribute to architectural idea. The case also shows a nonlinear and open-ended approach that focuses on the independence of form-finding, material design, and structural design. This is the end of my presentation. Thanks for listening.